Okay, our next speaker today is Chris Barnhill. Chris is the Director of Marketing at Skyven Technologies, an energy as a service company, pioneering in cutting-edge Arcturus industrial steam generating heat pump. Prior to joining Skyven, Chris spent 12 years in the industrial valve industry, where he led innovation teams to help solve challenges and improve plant efficiencies. Chris has an MS and a BS in marketing from Clemson University. Us chemical engineers welcome you to the stage.
Thank you very much. All right, if anyone was here to see Jim Saccone speak, we did a little bait and switch. He was on the site for a while and had a last minute change. So appreciate everyone's time and here. So thank you, Gary. Let's go. So yeah, the focus really here today all around energy efficiency, right? Anyone familiar with steam generating heat pumps? Heard of them? A little bit. All right, that's good. Probably residential heat pumps. They seem to be a little more on top of mind in Europe and here now as well. But we'll look at kind of how a steam generating heat pump can improve efficiency, reducing operating costs, and at the same time reducing emissions as well. So I'd like to start with just a fact. 20% of global carbon emissions are caused by industrial heat, and half of that is from steam. So industrial manufacturing is driven by steam. I'm sure we all know that. But emissions come from that. So it's a big area, and 3, 5, 7 years ago, that was a big focus, right? We're going to cut our emissions. And today, I think that's still the case, and then maybe it's just said a little differently now. But fossil fuel fired boilers, they've been around for hundreds of years, right? That's always been kind of the only cost-effective way to generate steam to run an industrial process. So there's been, and Grant kind of mentioned it too, with the price of gas here, it makes sense to use it, right? But you've seen a lot of manufacturers as of late committing to decreasing their emissions. And like I said, 99% of industrial steam comes from fossil fuel fired boilers. So what are kind of the options today? You've probably heard a lot of these. You've got electric boilers, renewable natural gas, but a lot of times those are going to be 3 to 5 times more expensive than just what we're paying for natural gas today. And then you start to get into this heat pump conversation. So there's a lot out there, a lot that can do kind of low pressure, low temperature, which have a fit in some facilities and some manufacturing facilities. But a lot of them cannot produce the steam at high enough temperatures and pressures to really be usable from a steam point of view. So when you look at kind of steam generation technologies and the economics to go around it. So if you're looking to, the way to kind of read this chart is the cost associated with removing a metric ton of CO2 or greenhouse gas emissions. What's the cost to do that with this new technology that's out? So a lot of people looking into hydrogen, great option for a lot of people and a lot of processes. Roughly $500 per ton of CO2 is the cost you're paying to reduce that ton of CO2. So as you work your way left here, you've got, and this is compared to natural gas boilers. So you've got renewable natural gas, similar situation. Pretty decent step change when you introduce electric boilers. The cost to remove that CO2 is a little cheaper. Thermal energy storage, maybe you've seen heating these bricks that store the heat, and then you can use that kind of on demand when needed for process heat. And then here we have Skyven Arcturus here, but when you start to talk about steam generating heat pumps, you get closer to that zero line, right? Which is ideal. And we'll talk a little bit about how there's an opportunity to go negative and actually do this profitably, which is always a nice option. So what does Skyven do? May or may not have heard of us, but we deliver emissions-free steam at the lowest cost possible. And we do that with no CapEx required, which is an important piece. And we'll walk through kind of how that's doable, some of the kind of applications that this technology makes sense for. And again, feel free to stop and ask questions or hold them toward the end, or I'll be around a little bit after to have conversations as well. So just quickly, Skyven Arcturus steam generating heat pump. Again, this is similar to Grant, not necessarily meant to be a sales pitch, but just want to educate on kind of what what we're doing and the technology that is available. So emissions-free steam, and we're using electricity instead of natural gas. So industrial electrification is a big topic right now, and that's what we're using. We're able to leverage high coefficients of performance, which we'll talk about here in just a second, to really counteract that price differential between electricity and natural gas. Obviously, that's the first thing everyone says. Well, natural gas is so cheap. Why would I entertain electricity to do the same thing? So now outside of the U.S., there are many places where it makes sense very quickly to electrify, especially with the high COPs and efficiencies that we can bring. So with our technology, right now we're capable of generating steam and pressures up to, or temperatures and pressures up to 420 F and 300 PSI. I was talking to Angel earlier. I know there's a lot of people in the room where you need higher temperatures, higher pressures in some cases, but we do have the ability to also just plug into direct use of a process. So in some instances, we're plugging right into the steam header into the facility and doing it that way, but we can also go direct to point of use of the steam if it's a specific application that these ranges fit. That's an option as well. That actually improves the COP quite a bit as well. Steam flows, one system goes from anywhere from 20,000 to 200,000 pounds an hour of steam. If more is needed, we can add additional systems, kind of just as a train, essentially, as a way to think of it. And what we're doing is we're capturing waste heat. So any facility, at some point, that steam is no longer usable. If it's from a temperature standpoint, pressure standpoint, most of the time, vented out to atmosphere. We capture that waste heat and then put it back through our system. There's some heat exchangers and a few other things involved. But take that and put it through the heat pump, and we're dumping out boiler quality steam, same temperature pressure quality that the facility is using today, and it's emissions free. Yes, sir.
Talking saturated steam only? Yeah. I'm assuming no superheated steam, just all this is saturated steam?
Yeah, sure.
Okay.
That's fair way.
Sorry, just making sure.
Yep.
Am I jumping ahead? But you haven't mentioned how this could, I was just Googling, this could be used for microgrids, community microgrids.
It's a,
Where you can't cite gas generation.
I don't know if it's in here, but it's a good question. And data centers and all these things come up, right? The waste heat source, if there's a waste heat source available and somewhere that needs the steam, then it's doable. So a lot of times we'll see maybe a lot of waste heat at a data center, but they don't necessarily need the steam back in, right?
Community side, could the waste heat be from a recycling center?
If the temperature is there, yes. Around 80, what we're saying 80 to 85 F waste heat source temperature, and then we can go from there. And we'll get a little bit, there are a few things coming that I think will help answer that question.
Thank you.
And then the last point, which we'll hit on here a little bit more in a bit, is we install this, we call it a hybrid configuration. So existing steam generation technologies, if it's natural gas boilers, if you're buying steam over the fence, whatever you're doing, that all stays in place. So that's kind of a redundant steam generation system there. And really that's all about reliability. And we'll talk about how that kind of reduces cost and improves reliability to leave those systems on site. So quickly, COPs, coefficient of performance. This is kind of how heat pumps can offset that natural gas price, right? The efficiency factor. We operate at a Carno of 78%. And we do that really through our multi-stage open cycle MVR, mechanical vapor recompression kind of architecture with low impeller speeds and some desuperheating along the process. So that's kind of how we're able to get to that level, which you can kind of see separates what we're doing from some of the other heat pumps out there. And that also our setup allows that higher temperature lift. So when you've got that waste heat coming in, right now we're able to lift that heat up to 330 F lift throughout the process. So another look at just some examples of different kind of heat source temperatures and then some process generation on the right side here and what those correlated COPs would be. So a lot of times you're seeing 2.7 to 3.4 is a typical kind of COP for this. But having said that, we have a project in basic engineering right now that's showing a 7 COP at. So again, it's all about efficiency and makes these things make a lot of sense. So We can dive deeper into this later if we need, but just quickly back to the redundant kind of what we call hybrid configuration. So again, installed in parallel with existing steam production. So on the right here is kind of a quick look at a facility. So that boiler house, everything there, the process, all that stays the same. There's no modifications. We're considered an external retrofit. So again, no impact to operations during construction or operation once we're flipped on. And again, we're just increasing the steam reliability. And we're doing base load operations. So typically 80% of the facility demand is typical, but it can be different in different places. And the real way we can say, hey, we're generating the lowest cost steam at all times is due to this hybrid configuration, what we call fuel switching. So again, we're installed outside of the facility, and the last point there is siting flexibility. We can be up to a half-mile away from the facility, which is nice in some cases. But the fuel switching is the facility can use electricity, obviously, with the steam generating heat pump Arcturus to generate their steam. If electricity prices rise, the grid is strained, whatever the reason is, Arcturus can work itself down. The facility flips back on. The boilers are in low fire mode. They come back on. And the facility itself sees no difference in the steam that's going through the process. So we'll go a little more detail in kind of how that actually works and the benefits of doing that. But that allows the lowest cost steam at all times. Yes, sir.
When you say natural gas, and I'm assuming that's also biogas and gas, renewable natural gas if it's high quality.
When I say natural gas, whatever they're using for their current steam generation, could be a natural gas boiler, it could be anything, could be renewable gas today, it could be an electric boiler that they're already using possibly, but whatever they're using would stay. Their existing steam generation stays on site. And then the other point here is we do use water as the refrigerant. A few positives, obviously, from an emission standpoint, 0 GWP, highly efficient. The only downside to water is a little bit larger of a footprint needed to do the compression and things to get the steam up to that temperature. But overall, the benefits outweigh that minor thing. And we looked at a lot of different refrigerants, and that was the one that made the most sense for our system. So I know it's a lot of engineers and technical crowd in here, but I did mention up front about how we do this with no CapEx, which is a big hurdle with a lot of these projects, right? Energy efficiency, emissions reduction projects. A lot of times they don't get to the top of the list on the CapEx dollars. So a lot of times maybe start the year there and they kind of work their way down for other projects to keep plants up and operating. So the way we approach this is, one, we align our financial goals with the emissions reduction goals at the facility, and then we fund the project. So there's no capital expense to the industrial manufacturer, and we do that by grants, incentives, federal, state level, different incentives. Could be at a utility. A few years back, we had a large utility incentive that helped a project go through. And then we also go out and get third-party project financing. So all of that's on our side. No capital is needed from the manufacturer. And then how we do this is the net economic benefits that are realized. We share those savings over the life of the contract. So if it's reduced, then I'll get to a slide. I'll hold that comment so you can visually see what that looks like. But 3 implementation models that typically make the most sense for our customers. One, this energy as a service model is really that's the side that no CapEx is required, right? So there's 2 kind of options there. Shared savings model, where we, Skyvent, are the owners of the equipment and project itself. We fund it, we install it, we operate it. We go out and procure the electricity, which we'll touch on here in a second. And then we share those net economic benefits. And then the second option here is a tolling model that you may be a little more familiar with. Pretty much all stays the same. Skyvent or the customer can go get the electricity, and then the customer is just purchasing the emissions-free steam directly from us. And then the third option, typical normal CapEx project. And we do have some customers that would prefer to go that route, which is perfectly fine as well. So when we're talking, I won't spend much time here, but when I say kind of this net economic benefits on the light gray here, you see different types of benefits. Obviously, avoided natural gas costs for the steam production or whatever you're using, or if you're purchasing steam today. Demand response revenue, which we'll talk about here in a second when you're on the grid, and then anything else that comes up. It could be buying CO2 credits, whatever, or selling those. It could be a bunch of different things. That all goes into the model here. Take out the operating cost, and then of course we have our net economic benefits that we'll share across the life of the contract. So electricity procurement, obviously that's a big thing, right? When you're doing industrial electrification, there's power needed, and some facilities have the ability to do that today. Most of them don't have the excess power and lines and transmission needed to do some of these things. So the way we've kind of approached it with customers, one, we go in looking to eliminate demand charges. So avoiding those coincident peak periods. And I have a chart here to show this, but that's where we can switch the heat pump off, and steam production just reverts back to the original steam if it's natural gas, if it's whatever it is. Step number 2 is negotiate index pricing. So we'll talk to utilities. Obviously, this is different everywhere within the U.S. and states, and then obviously outside of the U.S. if you're regulated, deregulated markets. But we're looking to secure a rate structure based on locational marginal pricing or LMP, and so we'll pay the utility that plus an adder. So most of the time it's still favorable because again we're a flexible load. We can turn off. We're not on at all times if we don't need to be. So usually a pretty favorable conversation there. And then 3, this whole point of all of this is to be able to operate in that hybrid mode. So switching off the heat pump if needed, if electricity prices rise, or at times when the grid is strained and the utility says, hey, we need power, we'll actually pay you to turn that thing off. We can do that and kind of reap those demand response dollars. So when we're looking at this kind of hybrid operations, when the electricity and natural gas prices here is the example, and this is done at each project because it's different at every facility. Electricity prices are different, natural gas prices here and there. But we will set a fuel switch strike price. So this is the black dotted line that goes across for this example right at $30. So when electricity is below that, Arcturus, the heat pump is on, delivering emissions-free steam, doing everything it's supposed to do, high efficiencies. If the price of electricity, for whatever reason, jumps up over that fuel switch strike price, the on-site boilers kick back on and generate the steam. And again, the facility itself doesn't realize this is happening. The steam generation continues. We've got sensors and controls that are monitoring the price of these in real time. The Arcturus system can ramp down in 1 to 2 minutes or less. And during that time, the boilers are in low fire mode and they're coming back up. So there's no drop off in steam. So the process itself continues. And that's kind of how we're saying, hey, you're getting the low cost steam at all times from an economical standpoint. So just quickly, kind of in summary, then I have a little case study to show as well. So kind of why our model proves value. Again, it's all about being profitable, low risk, we'll say emissions reduction. But it's proven technology, right? The bulk of our heat pump is built around mechanical vapor recompression. This is technology that's been around, proven in industry. And we kind of have this institute guarantee, right? It's our money, and this kind of rolls into the next bucket here too. But if our system's not performing, if we're not generating emissions-free steam, if our customer's not saving money, we don't get paid. That's where those shared savings come in, right? So if there's no savings happening, we don't make any money. So we're very much incentivized to make sure the equipment's running like it's supposed to be doing. Obviously financially attractive with no capex if that's a driver for you. And then the high COP, right? The efficiencies that we're seeing out of these systems really can counteract and go above and beyond that electrification expense. And then no impact to operations. Obviously, this is a must-have in manufacturing, right? We can't be taking the facility down. We can't be impacting the operations. We can't be hurting the steam quality. All of these things are obviously very important in projects like this. So no downtime, seamless integration. We're plugging into really 2 spaces if it's the steam header or directly into that use case of a process and plugging into the waste heat, capturing the waste heat. So I'm not sure if I mentioned this earlier, but we'll build this on site and then we're plugging into those two places. And the facility never comes down during any of that process. So a few case studies here. These are real projects that are in engineering phases right now. So I won't read all these. I'll actually start with the middle one. So a chemical facility in Germany. So we've got a waste heat source listed there from their vapor condensers. That source temp is around 185 F. And then when Arcturus is on, we're generating steam for this facility at 46 PSI, 294 F, at 152,000 pounds an hour of steam. And a COP at this facility is coming up at 3.54. And so with Skyven Arcturus for this project specifically, we're looking at emissions reduction of over 42,000 metric tons a year, and an average annual savings of $3.1 million. So that's noticeable money that goes into their pocket. They can reallocate it to the facility. They can, I don't know, pay their shareholder, whatever they need to do. It's their money. That's the takeaway there. And then an ethanol facility. I was talking to someone before. Ethanol has we've seen some success with the processes there, and for this example here, capturing that waste heat off of a dryer exhaust at 205 F, and then putting it back in at 150 PSI at 366 F with a COP of 3.42. Here, compared a little less savings, but on average, $1.1 million of savings each year with about 30,000 CO2 emissions avoided. So would love to have a conversation with you, your customers, whoever, to see if your facility, if it makes sense, if there's an opportunity to do that. I didn't touch on this. How am I doing on time? Okay. Okay, great. This is the last slide. So I didn't mention this, but the kind of the kickoff point of working with Skyven is what we call Galileo. It's a software modeling tool that really cuts front-end engineering down by 90+% from a time and cost standpoint. And what we're doing is we're gathering information about the plant, the steam, kind of boilers, the price you're paying for gas and electricity today. So anyone that's knowledgeable about the plant can answer these questions. We're doing this live on a call with them. And at the end of that call, we have essentially a mini project proposal showing, hey, with this steam generating heat pump, you can save X amount of emissions, dollars. Here's where it would go. Here's the waste heat, all those different things that we just kind of walk through. We're printing that out within an hour of a phone call. So we have a pretty good idea if it's worth to continue the conversation or not from that point. And happy to do that. No cost for that. Happy to do that for any facility or process that you would like to look at. From there, we go into signing the contract, right? So for us, we call it a Thermal Energy Services Agreement, a TESA. And then once that's signed, you've got about, we'll say, roughly 2 years until emissions-free steam is being delivered to your facility. It is a stage gate process. We'll obviously kick off with some engineering feasibility. I apologize for the typo there. But at each of these stage gates, so engineering feasibility, basic engineering, detailed engineering, we will go through a full engineering review and a economic review. So if anything changes during that time, if the project becomes uneconomical, we're not seeing the savings that we both intended to have, customer can cancel, no cost. If it's an engineering thing that needs to be changed, we'll fix that on our own at our own cost and continue the process there. So once all those approvals happen, we're ordering equipment, we're building on site, and we're plugging in and going. So like I said, would love to, if you have a facility in mind or a customer or anyone you know, would be happy to have that conversation. To date, a lot of where we've seen some success, ethanol, like I mentioned, chemicals, ethanol, pulp and paper, large food and beverage at times, textiles, really anyone that's using a decent amount of steam on a kind of 24/7, 365 basis. So universities come up quite a bit. For the most part, have the right parameters, but it's very seasonal. So a lot of times it doesn't make sense. There's not enough steam needed on a consistent basis. Which that kind of, I was trying to get to your point on the kind of capturing and using it more of like a district heating kind of standpoint. We have looked at that, and it really boils down to that waste heat's available, and there's somewhere for that steam to go. So if it's there and it's within a half mile of the waste heat source, it could be doable. We'd love to take a look at it. I think that's it. That's obviously not my name, but feel free to reach out to Jim or myself.
More questions? Oh, boy.
How fast can this spin up and down for steam production?
So
Repeat the
oh yeah,
question.
so how quickly can we spin up and down? So going from the electrified steam production back to existing.
Yeah, so for example, like, oh shoot, my boiler trips, how fast is
So it's up within 2 minutes max.
the, and sorry, on like the steam production, like it got for
So
idle, basically nothing to what in 2 minutes?
So, well, let me put it back this way. So the facility's up and running, right? There's steam being used. We're capturing that waste heat. Once that's plugged in, we're generating steam. So if the Arcturus system goes down for whatever reason, if it's price wise, electricity price, whatever, that'll can shut off in 2 minutes. Those boilers are up.
Yeah.
They're in low fire mode. Same the other way. If and those sensors are talking, so we're measuring that pressure at the header or at the point of use. We're saying 2 minutes either way to go full up, but there's no gap in between that steam.
So essentially, it's like similar to a standby boiler in speed.
You could say that, but we anticipate being up and running 85-95% of the time, even with that.
Yeah. Yeah, it's
The
not your
other way.
backup system.
Yeah, exactly.
Yeah.
Exactly.
Oh, it's just interesting to know how it goes in and out.
Sure.
Okay.
You ever report the conversation regarding contrasting cogen?
So the question was around cogen. Yes, and it's funny. So my background in industrial valves a lot was with power plants and large control valves and kind of Hersig, right? Heat recovery steam generator. To me, it's a very similar concept. And when I came over here, I was like, isn't that kind of like that? There's opportunity. I think what we've got to look at again is the waste heat source. I think you could get, but then where does that steam go from there? Would be something we would look at. But we've had those conversations in a few very obscure applications. But yeah, we would have the conversation for sure.
Okay, we'll get back. James.
Have you worked with any new construction facilities, or has all been existing facilities?
It's a great question. So the question is, have we worked with any kind of new builds versus retrofitting existing facilities? We haven't. We've had the conversations. There's definitely an opportunity there. And I think there's also the opportunity if you're doing a new build to implement the steam generating heat pump and maybe some of the other technologies that are out there too, right? So maybe not implementing a coal-fired boiler or something from the beginning, but the heat pump, maybe there's some thermal energy storage, maybe there's something else. But yes, it's definitely an opportunity that we could do that.
For the CapEx option, do you have a range of ROI or like a range to go?
So the question is around ROI if you go the CapEx option. So obviously our normal response is we go the energy as a service route. There's really no ROI because there's no money. A typical contract, I will say, is 10, usually 15 years. But that doesn't necessarily mean it takes that long to pay off the equipment. That's just the contract for the shared savings. I'll say on average, and obviously these are on average, 30 million-ish is probably a good number. From an ROI standpoint, you would run the numbers to see what those savings look like and see. But that's rough numbers.
That 30 million over the life of the equipment?
For 30 million for the project,
For the project.
from front to turning on. If we go the CapEx route, would be rough estimate.
How does the heat pump compare to an electric boiler? Because you talk about ramp up, ramp down time. And also you mentioned savings from a perspective of GHG perspective or from a natural gas perspective. How was the savings evaluated?
Sure. So the question was around how does it compare to electric boilers? And then also how do we kind of calculate when we say savings, what do we actually mean? So from an electric boiler standpoint, definitely a use case for those in a lot of places, right? The big difference there, their efficiency kind of 0.99 of a COP as a 0.99 is the most they can do, and natural gas boiler for reference about 0.83. So that's where the limitation comes. And a lot of times with electric boilers, you're gutting your whatever you have today, right? And that's now your sole source of steam generation. Does that answer that question?
So essentially is, yeah, but you're saying that the electric pump is a way much smaller footprint than the
Then the heat pump,
electric boiler.
the electric boiler is probably a smaller footprint than the heat pump. Maybe.
Sorry, I could add to that, like, I think the time on ramp up, ramp down capacity, like, I think they can be kind of similar.
They're
I
about
think
the
maybe
same.
electric boilers are a little broader, just because there's more options. But if
Sure.
it's like an anode electric boiler, like, it's in the same realm.
Sure.
And I do agree, it looks like this is a little bigger footprint than if you did like an anode boiler to go fast.
So you're saying it's more beneficial from an efficiency perspective compared to an electric boiler?
Correct. Yes.
Okay.
And then
So
your
now-
question on the savings, so a lot of those savings are the realized savings from not having the natural gas savings for not using
Okay.
natural gas is one, but also the emissions reductions is a number that we could share as well. If we looked at a facility to see how much emissions you would save, based off of not using the natural gas.
More questions? Question about the maturity of the technology. So how do you have actually implementations in the field currently, and what sort of state?
So we from a Skyven Arcturus standpoint are at a TRL 7 currently. And that's based off, like I said, the MVR tech, that piece is proven installed. So we use that a little bit. There is a similar unit, not from Skyven, but from one of our partners installed in Hungary that's been up and running for 5+ years. A similar type approach. We have a demonstration unit opening outside of Dallas, and hopefully June is the plan, which kind of gets you to that TRL 8. It's demonstrated. It's using it's a full scale system. And then our first system should be installed and operating in 2026. And that's an ethanol facility that's public information. Ethanol facility up in New York will be the first installation in the US for this product.
With that, thank you very much.
Thank you.